now it's a turn of Andreas Fring from City University, London, and which, by the way, we thanks also for the fantastic footage of the landscape of Afunalwe with the drone that you see in the videos is from the Andreas drone. So thank you for that, for sharing that. And he's going to talk about n-extended Lorentzian Kac-Moody algebras and their associated Toda field theories. So please, Andreas, go ahead. I will let you know after 10 minutes.
Okay, thank you very much, Francisco and everybody else, for inviting me and for organizing this really quite extensive conference. So what I will talk about is a joint work which I've done in collaboration with my PhD student, Sam Whittington, and it's about these two works. And the first one is about the mathematics of this work, and the second one is a physical application. Yeah. So what is the part and the whole here? Yeah, so maybe the part can be, we all know about finite dimensional Lie algebras, yeah, but we also know that this is not the whole. Yeah, we need some more. And if you think about string theory to describe the symmetries, you need infinite dimensional Kac-Moody algebras. But this might even not be the whole as well. So more recently, people found theories for which these symmetries are not enough. And one needs Lorentzian Kac-Moody algebras, which are extended versions of Kac-Moody algebras, and I will explain what that is. Yeah. So we were inspired by this mathematics, so I will not talk about the whole, and I will not even talk about the part. I will talk about the small part, and I want to talk about using these algebras and this mathematics to define Toda field theories. So Toda field theories are well known and really well studied, possibly the best studied scalar field theories in 2 dimensions, and there are various versions of them. So they have this potential here, and if I start this sum here at a equal 1, so the upper limit is kind of the rank of the algebra, I will get a conformal field theory. And if I start at 0, then I get a massive theory, which corresponds to Kac-Moody algebras. And one further distinguishes between beta real, when we have no backscattering, and in this case, the bootstrap equations are central, and one has managed to construct the entire scattering matrix to all orders in perturbation theory. That's sort of my claim to say they are some of the best studied theories and really well under control. When beta becomes purely imaginary, and you have a non-emission Hamiltonian or Lagrangian, then you have backscattering, and the key equation to determine the scattering matrix is the Young-Baxter equation. And mathematically, that's interesting because solutions are described by quantum groups. Yeah. So the question here is, can we also have A-1, A-2, etc.? Can I extend this? And I have to explain what that means. What properties do these theories have? And in particular, with regard to the previous models, I didn't stress that they are all integrable, and that allows us to solve them to such a degree of precision. Are they integrable? So here is something well known, and all this understanding and extension is based on Dynkin diagrams. So in the finite dimensional case, it's well known we have our simple roots. They can be encoded into a Cartan matrix, or they can define a Cartan matrix with the help of a Euclidean inner product. And then the entire structure is encoded of the Cartan matrix is encoded into a Dynkin diagram. And there's also an associated algebra to this. Now, if we go to infinite dimensional algebras, we add one root, alpha 0 here, which is the negative of the highest root. Yeah, these integers n are called Katz labels, and they're well known. So that means to each of these diagrams, we attach an additional node, and that is well defined, and we have affine algebras, and there's also an associated algebraic structure to this. Now, can we extend this, and what does it mean? Yeah, so there are various possibilities, and one famous example is E10, where one attaches another root to alpha 0. And that's E10, or this is an E8 diagram if I look at this from a finite point of view, and we can continue. We can add another one that's called very extended when I add another root to this alpha -1. Then we get E11, which is meant to be very important in type 2 string theory. And the question is, can we go further? Can we add more? And this is actually not known. The mathematics of this hasn't been developed. So in our first paper, we attempted to understand the key features of these models. So first of all, we require a root space. And the problem to find the root space is that inevitably here, because of the eigenvalues, you need a Lorentzian metric. And they are very, very complicated constructions for E10 and E11. But this one, based on this paper by David Olive and collaborators, allows to extend this in a very systematic way. And what one does here is one has a self-dual Lorentzian lattice, and if I have two-dimensional vectors, we define a Lorentzian product in this way. So there is a null vector or two null vectors, and there are two vectors of length 2. And this allows us in a very systematic way to add roots now to our finite dimensional system. So one redefines the highest root by adding a k, but that doesn't change anything because k has 0 length. And then we get here this extension over here. We have an additional root alpha 0. And the root alpha 1 is just added like this by defining this length 2 root. And then we can continue and we can construct. So this is now our proposal. We just add more and more of these spaces, and these are our simple roots. And these were the roots. Remember, the motivation is to use them in a Toda field theory. So we are able to formulate the Toda field theory. Now, how to construct the rest? We also need weights. So weights are the dual spaces. These are the vectors which are orthogonal to the alphas. And we also managed to construct them, and we found a nice closed formula here. So that's possible. We have all the weights. And what we also need is the Weil vector, which is the sum of all the weights. And this gives a nice formula involving the Coxeter number. I should say these are not rigorous proofs. Yeah, we solved this for very high n. Mathematicians wouldn't consider this as a rigorous proof, but the formulae work on Mathematica. We have shown this up to very high order of n. We are very confident that this is correct. And then we can also construct the inner product of these two Weil vectors, and that gives us what is known in the finite case as the Freudenthal-de Vries-Strange formula. And our formula, the formula we found, also reduces to that case. Now, key in the understanding of the finite dimensional algebras as well as Lorentzian algebras is the presence of either an SO3 principal subalgebra or an SO1,2 principal subalgebra, which are defined here. And they are distinguished by the feature that this number d here is either positive or negative. And we extend this property also to our n-extended algebras. And that will allow us now to study decompositions of these algebras. So when you add more and more roots, the question is what happens? Are they still objects which have consistent structure in itself? And what are the properties of these principal subalgebras? And as it happens, this number d here, yeah, that's in this case is d and in this case is d hat, can become 0. And that's a signature for the algebra to decompose. So here is a 2-extended D25 algebra. And there is 1 0 root here, or not 0 root, sorry. 1D becomes 0. And in this case, the algebra then decomposes into D18 and into a 1-extended E7. So one can systematically study this. Here's another example. You can have also triple decompositions, as in here you have two zeros, and it decomposes into a 3-extended E6, into a standard A finite A18, and into an A4. And what we have done is, so this first part of the work was just mathematical. We studied decompositions of these algebras. And we have done this for all finite dimensional algebras. So here's a table for all possibilities for the D algebras. So this D is really the algebra, it's not the D number I defined above. So these quantities allow you to get really an understanding of these algebras. Yeah. So what about the application now? So here's my Lagrangian again for the n-extended Toda field theory. Yeah. And this product here now needs to be changed. Yeah. So the product here of the roots, the simple roots, yeah, now we have extended this, so there are more simple roots now than in the affine or the finite case. We are summing here from minus n up to r, where r is the rank of the corresponding finite algebra, which we extended, and this inner product needs to be changed and is defined over here. Yeah, so that corresponds to these spaces here. Yeah. And here's a construction principle now. Let's construct a theory and see what kind of properties this theory has. Yeah. So I start with a G1 with a finite dimensional algebra, and that's well known. That's a conformal Toda field theory. And then I add now the affine root, and I add also this null vector, which doesn't change anything at this point, and I will get a massive theory, an affine Toda theory. So up to here, it's all well understood, and they are all integrable models.
5 minutes, Andreas.
Okay, thank you, Francisco. So if I add one more root now, what do I get? Actually, it will be, again, conformal, which you can see because the trace of the energy momentum tensor is 0. The minimum of the potential is at infinity, and you can't construct a massive model. However, I can make it massive by adding another root, and then the linear term vanishes, and we have a potential around which we can expand. So here, I drew here this little dotted line. What does that mean? That means this root alpha 2 connects not just to alpha minus 1, but it also connects to alpha 0. Here you see here alpha 0 has a k, and this has a k bar, and the inner product of k and k bar is 1. Yeah, so that's what this means. Yeah, but this is a massive model which one can study now, and one can understand this as a sort of perturbation. So there's a whole area of people who try to understand now. Not just, so the initial sort of program was to perturb conformal models and get massive models. That would be up to here, yeah. And more recent investigations concentrate on what happens if we perturb also the integrable models, yeah, or maybe they are still integrable. Yeah. So here we may continue. So if I add here an odd number of roots, then we always get massless models. And if I continue and add another one, then I have a massive model. So I call them G circle here, or because they are not the n-extended ones which I talked about before. There are many possibilities here, but this is a very interesting one in my opinion. There are lots of properties which these other models don't have. Question? What are the properties? So here is the classical mass spectrum, and classical mass ratios are very instructive here. We know that the integrable models have the property that the classical mass ratios of the simply laced algebras, at least, they all renormalize with the same value. So the classical mass ratios are, in fact, the quantum ones. So classical masses are very, very instructive to calculate. And you can see here the mass spectrum of these different models. And you see here, if we add more and more particles, we make the n larger and larger, which means each time we add new particles. You see here the first one don't change. That's an interesting feature. And that corresponds to the fact that E8 actually has a stable non-crystallographic H4 compound. That's also already known for the affine models. And that survives, interestingly, that survives for all these models. So there's much, much more to be understood about these models. But an important question is, of course, to ask, are they integrable? Now, if you have a lax pair, which we have in many cases, you know it's integrable. If you don't, what you can do is you can carry out the Penn-Levy test, and the test sort of, the spirit of the test is that you find as many as many singularities as you have degrees of freedom. So this is a long calculation we have done, but I just boil it down here to the essence. And you can reduce the entire Penn-Levy program to the eigenvalue problem of this matrix here. 2 times D, and D is again this number, which was the inverse Cartan matrix summed over one entry, times the Cartan matrix itself. So strangely, it appears again, this number, in a totally different context. And this number we used before to understand the decomposition of these algebras. So this number must be a positive integer for the theory to be integral. That's the upshot of the Penn-Levy test, which I can't explain here. And here's the results. So only the affine theory is integrable and all the eigenvalues are positive, but the rest does have always negative eigenvalues. So the short answer is these models are not integrable, sadly. But still they're close to integrable models, and we believe they can provide this algebraic framework. So all these other models, they were first studied as specific examples. E8 is the perturbed Ising model, etc. And they were studied in this way, but the algebraic framework is given by Toda theories. And we believe that possibly the Lorentzian Todas, using Lorentzian algebras, can provide a consistent framework for perturbed integrable systems. So my conclusions, so we first defined a new class of Kac-Moody algebras. There's a lot not understood about these algebras. It's mathematically very interesting. There's still a lot to be studied. And we would like to know more about the algebras. Here we mainly focused on the root systems, but we would like to know also more about the algebras. And then in terms of the application, so this I already just mentioned. So the Lorentzian Todas provide a very systematic framework for perturbed integrable models. That's what we are hoping for to establish with more studies. And then, of course, if you want to really study these Lorentzian Todas, you should go further, study quantum correction, couplings, possibly construct scattering matrices. Yeah, we know very well how to do this in the integrable setting. Question is how to do it when we perturb this. How can we calculate form factors, correlation functions, etc. And then, since we have these root systems now, we could think about other models which are based on root systems. For instance, Calogero models, one can formulate nicely in a uniform way in terms of root systems, so we can just study them using these Lorentzian roots. So thank you very much, and sorry that I had to rush, but thank you very much.
Thank you very much, Andreas. There are several questions, so I think that Olaf was having first a question. So please, Olaf, we have 3 minutes for questions, so let's try to be.
Thanks, Andreas. That was very nice. In fact, I have been thinking about, Lorentzian Kac-Moody system for a couple of years. I can share some partial results with you if you're interested, but I got stuck at some point. Okay. My question is why you use just copies of pi 1,1. Can you just not add pi n, or some more general Lorentzian lattice?
Well, this seems a very systematic way to extend the root space. That's we looked around how to do it. Yeah, so you can start from scratch, and just try to find some inner product which reproduces the Cartan matrix encoded in the Dynkin diagram. Yeah. And there are some really, really complicated solutions in the literature. So Nikolai and collaborators, there's one group working on this, and they're really, really messy. Yeah. Whereas this one, to us, seemed a very, very systematic way. I mean, this is not the only way. Yeah. But this is sort of really nice because you see here the roots, you just add copies of this, and then you keep attaching this k j-1 to the previous one. Yeah?
I understand. Yeah, so but it seems a very special, convenient route into the higher Lorentzian spaces.
It's really, really convenient, and from what we have seen in the literature, it's the most convenient one. Yeah, there's one downside here, because when you study Todas, you would like the representation space of the root to be the same as the representation space of the scalar field, to match particle numbers with vertices on the Dynkin diagram. Yeah, that's what happens in the affine case and so on. And you want to maintain this. You don't have to, but then you give up the well-known framework, and it becomes more and more diffuse to understand these models as perturbed theories, perturbed integrable theories. Yeah. So what you do here when you add these, you add always a two-dimensional space, yeah, but you want to introduce only one particle, because I introduce one root, but I introduce two more dimensions, and that makes this a little bit awkward for some applications. So there might be something more suitable, but I don't see how you can do it by reducing the representation space.
Okay.
But there are more possibilities.
Thanks, Olaf. We are on time, but we maybe a short question. Mikhail was in the list next.
Thank you, Andreas. My question is, at the very beginning, you commented that in affine Toda model, when parameter beta takes real values, there is no back scattering.
Yes.
So this is something like what we have in quantum mechanical reflectionless systems. So, but we know that quantum mechanical reflectionless systems, which are closely related with multi-soliton solutions of KdV, these corresponding quantum systems can be constructed by application of Darboux transformation to free particle system. So my question is there any procedure to obtain, to construct affine Toda systems proceeding from massless scalar field theory?
No, you see here, the models which have no backscattering, so the simplest model would be the Sinch-Gordon model. Not Sine-Gordon, but Sinch. Yeah? And they have no soliton solutions. The soliton solutions you have when you have purely imaginary coupling. That would be Sine-Gordon and the generalizations. Yeah? So the simplest one with no backscattering would be, which has a bound state, because the interesting thing happens when you have bound states, when you have poles in the S matrix, that would be what is called the Bulov dot model. Yeah? That's one particle which can fuse to itself. Yeah? But for real couplings, there is no soliton solution. Yeah? The soliton part, the soliton models are the ones which have purely imaginary coupling. Yeah.
But in the case,
yeah.
But in the case of free particle, we can take we can take as seed states some states from physical part of the spectrum of the free particle, and in that case, we obtain some analogs. We obtain not reflectionless systems, but they will be some analogs of hyperbolic sine models you mentioned.
Yes.
So I suspect, or naively, it would suspect that there could exist some analogous procedure to relate the systems with.
Yeah, you see, when I write this bootstrap equation in Young-Baxter, these are all quantum considerations. Yeah, not classical. Yeah. So this is really constructing scattering matrices, not and the sort of classical solutions play a less important role here in this framework. So this is all part of what is called the bootstrap program. One wants an S matrix, and then one calculates form factors, and ultimately by expanding the correlation function, one calculates correlation functions in terms of this n particle form factors, but they are not fields. Yeah? So there's a sort of a switch from fields to particles. Yeah? So the fields correspond only here to the solutions of the bootstrap program. That's the philosophy here. Yeah? So it's a different approach. But what you have in mind is sort of construct partner models from this framework, and I'm sure this is possible. Yeah.
Okay, thank you.
Nick has a question as well.
Okay.
It's very quick. I don't know if the answer is quick.
Go ahead. Very quick.
Very nice talk, by the way. Very nice talk, Andreas. What about string theory? Can your approach lead to new gauge lattices in, for instance, if you try to apply this to heterotic type models? And
I think that the E10 and 11 is only scratching the surface of possibilities. Yeah. And that was kind of, it grew out of the fact that E10 is a hyperbolic Lorentzian. Yeah. Right. And they are well understood and well classified. Whereas E11 does not fall in this framework and you need to extend it. Yeah. Right. And Olive and collaborators, they have defined a new set of Lorentzian algebras, which are defined by, if you remove any root from the Dynkin diagram, it should decompose into a finite and an affine one. Mm-hmm. And it must contain an SO 1,2 principal subalgebra. That was their classification scheme. Right. But that's very restrictive. You know? So our algebras is a much, much broader framework. There are many, many more possibilities. So now we can turn it around and we can ask, so now look for the corresponding theory corresponding to these larger classes. Yeah.
And it may lead to some new vacua for M theory, for instance, or something like that.
Probably it will. I mean, what kind of properties will they have? Yeah. So in this sort of confined framework of Toda theories, we get really new properties. Yeah. But we are losing integrability. I mean, that's a very precious property we treasure and which is very powerful to use, but we are still very close. You know, we are not leaving that framework, so we can consider them as perturbations of these theories. Yeah, and something similar might happen in string theory, but I can't say more about it. Yeah, so it's now the job of string theorists to look for new models. Yeah.
Thank you.
So thank you very much, Andreas. We thank you again.